So good morning, everyone. Thanks for being here on time. I'd like to introduce to you, if you're not familiar with it, or give you some update on what can be done reasonably with population algorithms. In particular, I will be talking about population Monte Carlo, also known as population annealing. But I will also touch upon applications of this scheme to other simulation paradigms. In particular, I will be combining the population idea also with MD, and so I have some population molecular dynamics simulation, for example, which actually also works pretty well. So this is a collaboration with a number of people, and as Tom mentioned, it's spanning a number of continents also. And so these are not, this is over a certain period of time. Whoops, this is not doing what it's supposed to do. It is, it's over a period of time, and not everybody is involved in all parts of this project, of course, but I'll mention that as we go along. Okay, maybe I should take the pointer indeed, because this doesn't do what it's supposed to do. Let's take that's the problem. There's a dialogue here which prevents things. Yeah. Maybe not. Okay. Let's see where that works. That does work. Okay, cool. Right, I'm not sure if I need to stick immediately, but right. So, in general, possible motivation for using population algorithms could be, put in the context of Monte Carlo algorithms in general. And I put here some kind of overview of different components. I focus here on Monte Carlo for now. I will be mentioning the MD part later on. But as we all know, there's a large number of different Monte Carlo algorithms for various systems, starting essentially, or everything was starting more or less from the Metropolis Rosenbluth and Teller paper in 53, and then this algorithm works pretty well in a general sense, but of course many things can be improved, and so these improvements they could be put into I give it another try into two groups. One I call here driver algorithms. So this is essentially using different move sets, using different local or non-local dynamics to improve things, and most of those will be quite familiar to you. For example, cluster updates can be applied to spin systems like Ising models, Potts models, stuff like that. Also to certain off-lattice problems. For example, there are proposals of cluster updates for liquid systems, hard disk systems, hard sphere systems, etc. We will be hearing, we haven't heard about, but we will be hearing about lifting and event chains and things like that today. That's another type of driver algorithm that goes away from the reversible detailed balance type of behavior, diffusive type of behavior that is implemented in the Metropolis approach, to something that is at least partially non-reversible, and by that means hopes to speed up the simulation. There are things like, which were mentioned yesterday in your talk, kinetic Monte Carlo, which is a slightly, which can actually induce massive speed improvements at low temperatures, in particular when the event rates are relatively low. We heard about Hamiltonian Monte Carlo or hybrid Monte Carlo, as the lattice field theory people would have usually called it. I mentioned move sets for polymer simulations. This is particularly important. You have pivot moves, you have crankshaft moves, you have bond bridging moves, and so on and so forth, because it's difficult to make efficient or achieve efficient decorrelation for such systems that have hard constraints built into them, because that leads to very strong attrition. And of course, there are also algorithms for certain, that now happened, for certain, I made too many moves in the wrong direction because it's just turned around. Up is down and down is up. For special problems like percolation or long-range interactions, for example, you also have certain algorithms. And so from those, I would like to set apart algorithms which are in some sense, meta algorithms, I would like to call them, or generalized ensemble algorithms is also a name that is usually used in this context. And many of those, at least by name, you will also be familiar with, like simulated tempering, parallel tempering. Simulated tempering is maybe slightly less. It was the first of these approaches actually to be proposed, but it's not used very heavily these days, I think. Parallel tempering is used quite a lot, and I think we should be probably talking about that in one or the other contexts during the brainstorming or something like that later on. Multi-canonical and Wang-Landau simulations, they are essentially, I mean, this is a bigger class of simulations starting out from umbrella sampling and these things, which was also mentioned in Tom's talk yesterday. So essentially you have suppressed states in your configuration space, which are typically connecting states between two of the metastable states, for example, that you would like to connect, and you increase the probability of those states artificially by multiplying the weight, the Boltzmann weight with some artificial extra weight and amplify the states like that. Metadynamics is of a similar type. And so in this group, I would like to put the algorithm, the class of algorithms I'm talking about today, namely these population kind of algorithms. And one of the main motivation for using them over, let's say, these other algorithms is that they are particularly good for parallel computing, for massively parallel setups. And we do know that, well, parallel computing is kind of a topic of current interest. But before doing that, let me just motivate a little bit more why we need these meta algorithms in the first place. So why do we have to use this type of approaches? And this is essentially, in most cases, to have transitions that involve metastable states, and either the crossing of barriers or the tunneling under barriers or the avoidance of barriers, which is usually something that is not easily done with these types of approaches. I mean, so for example, if you do non-reversible updates, that speeds up the exploration of configuration space, but if there's a big energy barrier or big entropic barrier, you will not typically cross that using these types of approaches. There are some exceptions to that, so that this division is not perfectly clean, of course. For example, cluster updates, they can actually jump barriers in some sense, but more often than not, some system that doesn't have an obvious symmetry built into it, I mean, where the metastable states are not connected by a simple symmetry, then you will have a hard time finding a move set that connects these metastable states in a systematic way. And so you have to come up with some idea of how to cope with that. So especially if your energy landscape or free energy landscape looks rugged like this, so if you, not maybe only have 2 or 3 metastable states, but maybe have many metastable states. So the key word here that came up yesterday also is glassiness. So if you have problems of that type, then we need algorithms of this. Okay, and so yeah, connecting to parallel computing, we know that Moore's law has worked for like more than 40 years quite well, but over the last about 15 years or 20 years by now almost, the mode of how this has been implemented has changed. For the first few decades, essentially this worked essentially by increasing the clock speed of processors. And so, typically, I don't know, every 2 years or something like that, your clock speed would have doubled, or every 18 months or something. But then this leveled off, around 20 years ago or something like that. Just because, well, the power dissipated grows, I think, like the square or even the cube or something like that of the clock frequency. And so if you go on, then the power density becomes too large. You cannot take that heat out of your system easily anymore. And so it's not really practical to do that. So instead, what has happened, of course, is that now, starting from these times, parallelism has really exploded in some sense. Parallel computers existed before, but now everything is massively parallel. So for example, I mean, this is not perfectly up to date, but some of the recent supercomputer systems have millions of cores. And so also Now it's typically not possible for any single user to use millions of cores. That might be the case in a few years or something like that. And even now, thousands of cores or even 10,000 is something that you can routinely use in your application. So how does that work with Monte Carlo? Well, not very well. This was also something that you mentioned, Tom, that Monte Carlo, as it's in the simplest way defined, is a sequential process, right? I mean, you have this Markov chain, and so you have to essentially create one event after the other, and you cannot easily create all those events in parallel because each event depends on the predecessor events. And so it's not obvious per se how to do parallel computing for such systems. Obviously, if you have short-range interactions, one thing you can do is to use a domain decomposition of your problem and then compute forces or do updates in each of those domains independent of each other. And then you have to, of course, only look at what happens. I mean, so if this is like on a square lattice, one of those domains, you have to look at what happens at the boundary. You have to exchange information between neighboring tiles such that you have consistency across those boundaries. So this works, I should say, quite well, but of course there's a limit to parallelization that way. If your domains, I mean, if you really are in this era where you have millions of cores and then your domains for whatever system you might be wanting to study become tiny, where each domain only has a single particle or a single spin or whatever, then that's the end of parallelization. You can't go on to a larger number of parallel cores. And right. And so what other options are there? Well, parallel tempering has parallel in its name, so it should be suitable for parallel computing. And so for those of you who might not be familiar, the idea here is that you simulate a certain number of copies of your system, otherwise identical, at different temperatures. So these different colored boxes are the same system run at different temperatures, and then you do update steps, and every so often you propose an exchange of the copies typically sitting at neighboring temperatures. This is not not a necessity. You could also propose exchanges at a larger distance, but the largest acceptance rate will be for neighboring temperatures. And that way, copies can essentially make something like a random walk in temperature space. And so they can, if they sit in a metastable state at low temperatures, they can diffuse up to high temperatures, decorrelate there, and then walk back to low temperatures, typically ending up in a different metastable state. And so this is actually, this works pretty well. I mean, this is being used in glassy problems, thin glasses and so on, but it's also used in MD simulation for biomolecules and stuff like that. But the point is, it's not, in that sense, massively parallel. I mean, this is obviously a cartoon, but it doesn't usually make sense to have thousands of temperatures or tens of thousands of temperatures or something like that. And that is essentially, at least in part, connected to the point that you do a random walk in temperature space. And if you do a random walk with very tiny steps, you know that for performing a random walk, or for traveling a distance n, let's say, in a random walk, you have to make n squared steps. And so it will take a very long time if you have a million temperatures to actually come from the lowest temperature to the highest temperature. So this is not practical. And typically most simulations will use like 20 or 50 at most temperatures. So that's, again, no match for a million cores in your parallel machine. Okay, there are also, I will not talk about that here, but there are also ideas to, if you do this umbrella sampling or multi-canonical type of sampling, you can do that in parallel by essentially having parallel walkers that add up onto the same weight function, essentially, and like that, they contribute to the same task. So this works to a certain degree. Yeah, and so that's the background in which I would like to mention these population techniques, because I think they have more or less unlimited, in a certain sense of the word, potential for parallelism as compared, or at least much better potential for parallelism compared to the other approaches that I mentioned. Right, and so the basic idea is illustrated here in another cartoon that is deliberately similar to the cartoon for parallel tempering, because also the algorithms are, in fact, in some sense, quite similar to each other. And so what we do here is we have also several copies of the system, but this could be a large number of copies. I mean, we're talking about 10,000, 100,000, maybe millions in some cases. And in difference to parallel tempering, all of those copies sit at the same temperature. So this is again indicated by this T label here. So they sit all at the same temperature, and you start usually, I mean, this is the simplest scheme, you start usually at a high temperature, for example, even infinite temperature, where you could easily draw a perfect sample from the equilibrium distribution, which is just random configurations in that case. So you simulate each of those with whatever update you might have to hand. And then at some point you make a temperature step. So you cool the system, slightly lower temperature. In making that temperature step, you resample the population. So look for each of those copies. Some of them might be more likely to occur at a slightly lower temperature, and that is essentially how, I mean, this being more likely has to do with them having lower energy, at least if you're in the regular canonical distribution. And if that's the case, you might make a few copies, extra copies of them, or some of the configurations might be less likely to occur at a lower temperature because they have relatively high energy. And then you might throw them out of the population and continue without them. So this is that you might be interested in, whatever that is, in the ordered phase or whatever your problem is. So that's basically the idea. And so this was proposed, in fact, quite a long time ago. It's now 20 years ago. But for the first, something like 7 years, 7, 8 years, more or less nobody took notice of it. So in part, I think, because it was published in a place which wasn't super prominent in some sense, was published in the proceedings of a conference that was held for 50 years of Metropolis, the Metropolis algorithm. Some of you might have heard of that. There was a conference in 2003 celebrating 50 years of Metropolis. And so it was in the proceedings of this conference. And okay, proceedings are not maybe the most prominent place to publish something like that. So it took, some years until John Machter kind of reinvented that. And I think that's probably, I mean, at least that's the story he told me, that he had written the draft PRL that he wanted to submit. And then he, at some point close to submission, he discovered this article, or somebody told him about that. And so he was slightly frustrated. And so then it was published in PRE, I think, or something like that. Anyway, so this is the description of the approach. This is more or less what I said, right? I mean, you start with a population of R, the name of the population size, independent copies at a high inverse, a high temperature corresponding to a low inverse temperature, beta 0, for example. Infinite temperature could be useful in that case. And means that, I mean, in many cases that's simple. Of course, it's not always simple. If you have, again, hard constraints in your problem, if you have a polymer or something like that, it's not trivial to generate a perfect sample, equilibrium sample, even at infinite temperature, because you cannot break the bonds, right? In many cases, like in a particle system, it would be trivial to do. But even if it's not, if you couldn't generate a perfect sample from this temperature, it's still easy to create a very good sample like that, even so. Okay, then we do this resampling for a temperature step, and it's no surprise, of course, that you should do that. I mean, make extra copies or even kill configurations with a probability that is proportional to the ratio of the Boltzmann factors of the configuration in question at the two different temperatures that we're talking about. And of course, you have to normalize that properly to make up probability. Okay, and then, I mean, this is not enough formally, so you do need to do some local updates as well, because otherwise, you make copies only of the configurations that were present in the initial population, and they're unlikely to contain configurations that are relevant at low temperature. So you have to do updates in between, but this is all one can say. So what type of updates you do, this is entirely flexible, right? I mean, it could be MC, it could be MD, it could be any type, practically any type of MC algorithm or MD algorithm that is, that simulates the right ensemble at the temperature in question. And just to fix notation, so we typically apply, or the number of those updates, sweeps, whatever that we apply, this is called theta. So this is another parameter in the problem. And then, well, you know, estimates for quantities are now computed as population averages instead of time averages, as you would in a standard Markov chain Monte Carlo. And then you do that until you converge. So for the Ising model, for example, which you could use as a benchmark, this is an illustration of how this looks like. So this is, sorry, the labels are fairly small. So this is the internal energy as a function of inverse temperature. And what is shown here, so this is starting at infinite temperature. And so the purple set of dots corresponds to the energies of the individual members of the population. And the average essentially is then this green set of dots. And you see that, yeah, I mean, you move the population along, the width and the spread of this population might change as the temperature changes, because the width of the energy distribution depends on temperature. For example, at low temperatures, the width is much smaller, and you get your averages, your estimates as population average. Question is, the first question is, does that work? Does that give the right answer? Of course, this is why we first looked at it using the Ising model, because they're exact results even for finite systems. And so you can compare to something well established, for example, the specific heat shown here. And yes, if you look at the relative deviation from that for, I don't know, there's maybe, sure if it says here, it does say here it's like a 64 square system. And yeah, you get small relative deviations, like 10 to the minus 3 or something for a certain computational effort, like 50,000 copies. So that seems to be fine. But then if you look a little bit more closely, there can be problems if you choose the parameters in a way that is not appropriate. So it's not foolproof in the sense that you could use any type of parameters and always must give the right answer. So for example, what is shown here is again a series of such simulations for the 2D Ising problem, where we have different population sizes, and for each population size, different numbers of rounds of updates, sweeps that are performed. And this is arranged in such a way here that the total computational effort stays the same, right? I mean, if you decrease, or let's say if you increase the population size, you decrease the number of sweeps such that you compare the same computational effort. And one sees that, I mean, if you decrease the number of rounds of spin flips too far, you only make one round, for example, you start getting some systematic deviations, just because as you kind of pool the population, the number of rounds of spin flips is not enough to keep the system in equilibrium, right? And then it falls out of equilibrium. Yes. No, theta is the number of rounds or sweeps or whatever of updates that you do for each copy at a fixed temperature. So you start, then you make a temperature step, and then you do some updates to all of the copies, and theta is the number of updates in suitable units you do for each copy. Okay, so one needs to monitor this, so you can have, I mean, this is just for illustration, very dramatic deviations. So the difference between this picture and this picture here is that in this case, we didn't do resampling, right? So, I mean, you could also say, let's just do in parallel, some kind of annealing for each of the copies without ever doing any resampling. Formally, if you wait for long enough after making a temperature step, that's also fine, right? I mean, you make a temperature step, you re-equilibrate the system, and then you take a measurement. That's an acceptable Monte Carlo approach. Of course, the point being you have to do enough updates to then re-equilibrate, and these parameters, which are the same as in the previous slide, they're not enough to do that without the resampling. So if I just simply switch off the resampling, this is what I get. So I fall, even for all parameters that are chosen here, I fall out of equilibrium, and they never return into equilibrium, even for lower temperatures. So the resampling is really an important ingredient. Okay, and then, I mean, I will not go into that too much, but you can study in some detail the dependence of the approximation, let's say, on the various parameters like the population size, the number of sweep, let's say the sweep protocol, because nobody tells you that you should do the same number of sweeps at each temperature, and also the temperature protocol, right? I mean, the simplest thing which was also used here is to make constant inverse temperature steps, but this is also not necessary. You can do something more creative than that. And yeah, I don't want to spend too much. Yeah, sure. Absolutely, yes. Right. I mean, we will see that a little bit later on. So essentially, what is important for the temperature protocol is that you have sufficient overlap of the energy histograms, right? It's very similar to the parallel tempering approach. And this immediately tells you that, as it stands, it will not be very well suited for first order conditions if you have a latent heat such that you jump in energy, because then you couldn't guarantee that you have that overlap. Yeah. It's both. It's actually all of those parameters which matter. And I'll come to that just now in some sense. Yeah. Right. Okay. I shouldn't spend too much time on this, but just to mention, because I think it might also be interesting later on for the brainstorming. I mean, one important aspect of this is not a Markov chain approach as it stands, right? I mean, you go sequentially in temperature. You never make a step to higher temperature. So it's not like a Markov chain in temperature, something like that. So in temperature, it's a so-called sequential Monte Carlo algorithm. But inside of it, at least in the standard cases, I mean, this is also not a necessity, but often you would use a Markov chain algorithm to do this, the particle updates or spin updates or whatever it is. So it's a little bit of a hybrid approach in some sense. And so that makes it, from the formal analysis, a little bit difficult because it's a mix of two algorithms in some sense. So essentially what I shortly want to talk about is, what are the systematic and statistical errors? Yeah. That's right. Yeah. That's right. Yes. In fact, I mean, yes, in statistics, they have something that they call particle filtering methods, and they are very similar, or in some cases, they are identical type of approaches, in a different language, but they do essentially the same. Right. I'm not sure what you mean by match. I mean, in terms of the things that were considered in both communities, I guess the results are not in contradiction to each other, but there has been very little communication between these two communities in the past. I mean, so we've now started to look at some of these papers, and I know also that, for example, Arnaud Doucet from Oxford, he's been looking at these things from the stats side also. So there's a little bit of exchange, but it's also the case, one of those cases where you have parallel developments to a certain degree, and yeah, but it's there's some potential in looking obviously at the other literature from. Okay, right. So what about statistical errors at first? I mean, how can we estimate those? If you look at this sketch here, so the colors are beautiful, of course, but they also serve a purpose, and that is to distinguish things that are in the same ancestry tree, so to speak, which you could call families, essentially. And importantly, those families are statistically independent of each other, right? I mean, if you're in a different family, you haven't had any exchange of any sorts with another family, and so clearly we have statistically independent subgroup in, in each in the sample at a given temperature, and so these can be used for estimating statistical errors, and so you can look at certain things connected to the. I mean, there's this number of families, and you can also look at essentially the mean square family size and similar quantities, and people have done that. So, for example, this is the number of families. Again, for the Ising model as function of inverse temperature, and you see, okay, this first, decays exponentially, and then it settles down. I mean, the exponential decay is essentially because initially each family has only one member, and then so each time you cull away a copy that kills the family, so to speak, whereas later on you have families with several members, and so family doesn't die out if one member is removed. And then, interestingly, but also expectedly, close to the phase transition, which is here, you have a somewhat dramatic drop in the number of families, because then correlations really become important. There's critical slowing down, essentially, in this problem. And so this is the type of behavior that we find. You can also look at these other quantities. They behave essentially in a similar way. Yep. Right. Is that what you mean here? Yeah. Right. No, I think this is kind of connected to the parameters that were chosen here. The point is that if I had chosen theta to be the same everywhere, then I don't think you would see that. The point is that the biggest population here has the smallest theta, the smallest number of spin flips in between. And so that means that the effect of critical slowing down will be the most pronounced, right? Because you don't have, you cool, and you don't have enough time to actually re-equilibrate the system. And that means you fall more strongly out of equilibrium, to say it like that, and that creates more correlations, and that actually reduces the family size more dramatically. So it's really only because I chose to have r times theta constant in this step. Okay, well, statistical errors, they don't behave exactly the same. So we know that statistical errors are essentially proportional to, in the energy, are proportional to the specific heat. And we see, yes, it does peak at the critical point, but it also goes down again after that. And that is not reflected in the family numbers as shown here. Oops. So instead of just looking at the number of families, it turns out that it's actually useful to look at some kind of effective population size. And maybe let me just jump over some of those details. And so how do we define this effective population size? We make an analogy to the analysis of Markov chain data. So you know that in Markov chain simulations, if you want to estimate statistical errors, what you do is you typically directly or indirectly estimate what is called the integrated autocorrelation time, and that determines the number of effectively independent measurements in the system, right? I mean, so if you have completely independent measurements, then we know that the variance of the mean is just the variance of the individual measurement divided by n. And if there are correlations, then this n gets replaced by an effective population size, which is the original n divided by this integrated autocorrelation. So this is just a measure for the correlation in your Markov chain. And something very similar can be done here. Of course, it's not a time-wise correlation that occurs, but it's now a correlation between neighboring members of the population, right? I mean, if you're neighboring, then you're more likely to be in the same family, and so you're more likely to be highly correlated to each other than if you are a large distance away from each other. And so we can use this and then do some kind of blocking analysis. This is completely analogous to what people do in Markov chain Monte Carlo simulations just now, not with respect to time, but with respect to the replica index axis, if you want to call it. And yeah, I mean, I don't want to go into those details, but this is the effective population size, again, for the same problem. And you see, you start at the whatever chosen initial population size, and then, you know, you have a minimum close to PC, but then you recover also, because even at, you know, at low temperatures, at least as far as the energy is concerned, your Markov chain updates are able to actually re-equilibrate the copies. I mean, there's no critical slowing down in the ordered phase in that sense. So this is actually a good way to estimate statistical errors, and then you can deduce certain rules for how you should choose the number of them. Okay, just to summarize this bit, because I think it's a bit technical. So there's more analysis, and so we believe that we have good evidence, and we can show certain limiting behaviors, that the bias, the systematic error of this approach has the following asymptotic dependence on the relevant parameters. So this is for the simplest case where you make constant inverse temperature steps. So the inverse temperature step is this delta beta. R effective is this effective population size, and theta is the number of rounds of spin flip. And you see, so you retain the exponential dependence on the number of updates, spin updates or particle updates of the Markov chain type. And that's plausible, because if you plug in a Markov chain update as the updates to be performed on the individual replicas, then of course you still see Markov chain behavior in this parameter. But we do have a decay of the systematic error that is only 1 divided by the effective population size. So it's not an exponential decay. It's just a power law decay. And so we also have some description for the effective population size in terms of these factors. So in some sense, to a little bit answer, Beatrice, your question, how should I choose the parameters? One thing I will just now mention on one of the next slides is it's much better to use an adaptive temperature schedule instead of just doing fixed steps once you've done that. So that takes care of the delta beta parameter for the temperature protocol. Once that's done, you should choose theta to make sure that you remain in equilibrium at least until it's hopeless to remain in equilibrium. I'm thinking of the spin class problems or classy problems where, you know, below a certain temperature, you cannot hope to be in equilibrium. So it doesn't make sense to increase the number of spin flips further, but up to that point, you should do that up to the point where that allows you to remain in equilibrium. And then you should, with a fixed computational budget, maximize the population size that you have to get kind of the best estimates because the estimates are population averages, right? So that's kind of the rule of thumb that can be deduced. And so let me speak about a few improvements. And the first of those is exactly this adaptive temperature schedule. So if you make fixed inverse temperature steps, so delta beta, for example, is 0.01 or 0.02, and then you look at the overlap of the energy histograms at neighboring temperatures, then unsurprisingly to anybody who's, for example, done parallel tempering, you find that there's a minimum of this overlap close to the critical point. So that's a combination of two effects. I mean, the width of those histograms changes, but also there's a maximum slope of the energy as a function of inverse temperature close to the critical point. And so these have to be balanced. But so there is such a minimum, and that immediately indicates that you should choose more temperatures close to the critical point. And one way of doing that systematically would be to ensure that you have a fixed overlap of the histograms. And so that can be easily done, much more easily in parallel tempering, where also such protocols have been proposed. But for parallel tempering, you have to do pre-runs to determine the temperature schedule. Once you fix that, then you can do the final thing. Here, this is not necessary because you are at a certain temperature, and then you only need to decide what is the next lower temperature that you need to choose. But you do have an energy histogram at your disposal because you have a population of configurations. You can use temperature reweighting to predict what will be the histogram at a slightly lower temperature, and then you can use some kind of bisection search or something like that to choose a lower temperature that guarantees a certain histogram opening. So that's very nice. And if you do that, of course, you get a fixed overlap of within certain error margins. So this takes care of the temperature protocol. And then that leaves us with the question of how should we choose theta. This is also not something that necessarily needs to be constant over the whole temperature range. We could do this also adaptively. So for example, if you look at the effective population size as a function of inverse temperature, this also has this minimum here, right? I mean, this is the effective critical slowing down. So we can use this information to actually choose the number of spin updates such that the effective population size remains essentially constant over the transition. And if you do that, okay, there are different ways of doing that I mean, it's a control theoretic problem to do that reasonably, but you see if you do that, you get some kind of peak in the number of spin updates that you should do. And then if you use adaptive theta, this is exactly that, then you see that the effective population size remains more or less unaffected by the transition. Also, we can, for example, combine the data from all the different temperature steps that were made. I mean, they are substantially correlated, at least for neighboring temperatures, but still there's, it's free information that we can make use of by throwing it all into one big pot in some sense and analyzing it together. So this is the so-called multi-histogram analysis, which is otherwise also well known, of course, independent of population annealing. So if you do that, so this is, for example, the relative error and the specific heat for the Ising model from the same simulation, just analyzed once in the way that I've so far described, and that's the red data set, and then analyzed using all the histograms together, reweighting to one temperature point, and that reduces statistical errors without any additional simulation. Okay, and so there are two more things I want to mention. One is that is connected exactly to the issue of the multi-histograms. This algorithm comes with, let's say, a free estimator or an easy estimator of the free energy that is quite useful in many situations. I mean, one application is the combination of histograms, because you need free energy for each of those simulations to actually get the weight factors right. And so this estimator is shown here. What are these Qs? These Qs are the normalization factors in the resampling step. And you can convince yourself easily that the Q is something like an estimator for the ratio for different functions. And well, then you get this telescopic type of expansion in these factors, and that leads to this term here. And essentially, this is something like a more sophisticated version of thermodynamic integration, essentially, where you, which works formally, at least even for temperature steps that are not small. And so this can be used, well, for doing the multi-histogramming, but also for doing another thing that I want to tell you about, and this is weighted averages. So, I mean, ideally, you do one big simulation with a large population for your problem, and then take the averages as population averages as estimates for the quantities you're interested in. But sometimes this might be problematic for various reasons. Once maybe your system could be significantly big, such that you cannot simulate as large a population as you want because of memory constraints, for example. Or you make a simulation with a certain population size, but then afterwards you realize, oh, well, it wasn't perfectly equilibrated. What do you do? Well, you could start from scratch, of course, with the population size, but another option is to make another simulation of with the same parameters. And then the question arises, how should you combine those simulations together? Naively, you would say, oh, well, just average over the two, and that's it, if they have the same parameters. But this is not correct, because, well, there are essentially different free energy estimates for these two simulations, and you have to take those into account. So they have different weights. You have to take the weighted average to do this properly. And that can be done so you can convince yourself that there is a run-specific weight of this type. And so you should take a weighted average with weights that contain these free energy estimators for each of those simulations. And the free energy itself, of course, is independent, but the free energy estimate will be different for each simulation. So these factors need to be taken. And then, yeah, I mean, you can check that this actually works. For example, I mean, you have to do certain or keep certain things in mind for doing such weighted averages of non-configurational quantities, like fluctuation quantities, like just stability, specific heats, etc. But then you do see, I mean, this M here is the number of simulations with the same parameters, and you see that there's a systematic decrease of the, in that case, the systematic errors, the bias, as you increase the number of simulations. Okay, and that can also be done for spin classes. We played a little bit around with that, and then you can compare essentially the situation, and this is shown here, one simulation. So you make either one big simulation, let's say with 1 million replicas, or you make 10 simulations with 100,000 replicas. And it's clear that this one with 1 million replicas formally must, it can be worse than the average of the other. But the question is how different are they? And it turns out that for everything apart from the hardest instances, there's practically no difference. But if there's an instance where you have correlations that exceed, let's say, 100,000 replicas, then you can see deviations. So, but I mean, luckily one can control control for these cases. Okay, and so I don't want to show performance, but I want to flash two generalizations, or mention them at least. One is to quantum Monte Carlo that I want to mention, which we did for a system like the D-wave system, for example, which is essentially like a transverse field rising model. And there you can apply this essentially using a Trotter-Suzuki decomposition and do some kind of Monte Carlo of the effective classical system that you have generated from the quantum classical mapping of this problem. And this works reasonably well. So we have some data. This is currently under review. And one other application is to MD, which I mentioned at the beginning. So how can this be combined with molecular dynamics? Well, it's relatively straightforward. So instead of doing, let's say, MC updates in between the temperature steps for each of the copies, you can also do MD updates. The only thing, I mean, in that case, we did it for the NVT ensemble, but it could also be done for other ensembles. Importantly, of course, you need to use a stochastic thermostat in those simulations, because otherwise, if you make two copies, they will stay the same forever, and that's not useful, of course. But if you do that, it works actually quite well, and so we applied it to some test problems, for example, this pentapeptide system, which is a little bit difficult to simulate, and so this was also tested using parallel tempering, for example. So if you do a canonical simulation, you don't get good results, but if you use something like population annealing or parallel tempering, you get good results. And the interesting thing is with population annealing, if given sufficiently large computational resources, you can easily improve with the same wall clock time. You can easily improve the results, which is not easily possible with parallel. Okay, yeah, I don't have time to talk about microcanonical simulations, but this is a little bit interesting for what you mentioned about the first order transitions. So if you do it in the canonical ensemble, it's not a good approach, like parallel tempering isn't for first order transitions, but you can do it microcanonically, and then you essentially have an energy lid that you would sweep through the system instead of having a fixed temperature that you tune. You have this maximum energy that you allow, that you slowly reduce down to very low, I mean, down to the ground state essentially. And for that, you can easily, for example, look at something like a pot system or anything else with a strong first order transition, and then get back to the canonical ensemble and use reweighting in the usual way. For example, look at the sampling barriers and so on and so forth. Yeah, I should wrap up. Multi-canonical is another thing that we're currently looking at, and that's connected to sampling of suppressed states. And this can also be combined with population annealing approaches, but maybe I'll tell you another time. Okay, so just to wrap up, oops, that was not the wrap up yet. So in general, I think it's a nice, let's say, framework for doing parallel simulations. We have some code to play around with. So this is a code running on GPU for the Ising model that you can easily adapt. I mean, this is just the basic algorithm without some of the extra bells and whistles that I mentioned, but it can be a good basis for yeah, further improvements. Essentially, what are the advantages of the approach? I mean, of course, it's the parallelization that I mentioned, but some other aspects are that you get these free energy estimates, which are quite accurate, which are not at least provided in standard Monte Carlo. It can be made adaptive using these, adaptive temperature steps or adaptive time steps. This is quite useful. And it is, let's say, a meta algorithm in the sense that you can combine it with many simulation techniques, MD, QMC, and so on. Okay, I didn't talk about the resampling protocols, but just to let you know that there's also some optimization that you can do in deciding how should you actually do the resampling. I mean, the way I described it, you only have to guarantee that the expectation value of the number of copies you make is actually this ratio of Boltzmann factors times the normalization. But what the distribution is actually an open parameter, but it makes a difference which distribution you choose, and so you can optimize. And also the weighted averages seem a useful feature because they allow you, once you are done with your simulation, to actually make another simulation to reduce the systematic error instead of only reducing the statistical error, which is a good feature. Okay, and so with that, well, I thank you. I thank my collaborators, of course, and I point you to some references if you're interested. Thank you.